Welcome. In this mini lecture, we're going to cover the key idea from section 3.1, counting lists. First, there's some definitions we need to acquaint ourselves with. The first being a list. A list is an ordered sequence of objects, which for the moment we'll just denote with some dashes, separated by commas, and in fact, we'll put it in parentheses. So this would be an empty list at the moment. There's nothing in it. But we can add entries to our list, such as A, B, C, 1, 2. And that list is distinctly different from, say, the list 3, 1, A, B, C. In this case, the order of our elements matters. So, each list has entries. Our first list here has length 5. Our second list has length 5. An empty list would be denoted by parentheses with nothing in between. That's the empty list, and it's the only list that has length 0. Every other list will have some length. Now, we're going to examine many problems that involve making lists. So, for example, how many one-topping pizzas can we make if there are 2 crust sizes, 2 sauces, and 3 toppings? So, let us begin by thinking about this in terms of our first choice, the crust. There could be a small size and a large size. The next option we need to choose is our sauce. So maybe our sauce options are red and white. Lastly, we have 3 choices of toppings. So maybe our 3 choices are bacon, olives, and pepperoni. As we build each pizza, we see we can traverse each path here. We could choose, say, a small pizza with white sauce and pepperoni, and that would correspond to the list SWP. If we maybe chose a different option, say a large pizza with red sauce and olives, that would correspond to the list LRO. In traversing each path, we would see that there's 12 different pizzas that we could make. Now, creating a tree like this can be very time consuming, so we would like an easier way to do this. The multiplication principle tells us that for our list of 3 options here, of crust, sauce, and topping, for the crust there are 2 options, for the sauce there are 2 options, and for the topping, there are 3 options. So the multiplication principle tells us that if we multiply these 3 numbers together, we will get 12 possible pizzas. So let's consider another example. From our class of 27 students, in how many ways can 6 people be chosen to make the starting lineup, which consists of center, left wing, right wing, left defense, right defense, and goalie of a hockey team? So in this case, our list would involve the center, the left wing, the right wing, the left defense, the right defense, and the goalie. How many different people could be chosen to be placed into the center position? To begin with, there are 27 possible people. Then when we move to choose the left wing, how many options are there? We've already used somebody for the center, so now there's only 26 people left. As we continue down the line, each time our number will be decreasing by 1 because we filled the position with someone. So, in this case, we would have 27 times 26 times 25 times 24 times 23 times 22 possible hockey teams. So, that's a very large number. We're not actually going to compute it, but we know it's large. Another way we might consider writing this would be with factorials. So, what is a factorial? For example, if we're interested in 5 factorial, the exclamation point denotes factorial. That would be 5 times 4 times 3 times 2 times 1. So writing the above in terms of factorials, we could write 27 factorial over 21 factorial, because this would be equivalent to saying 27 times 26 times 25 times 24 times 23 times 22 times 21. We'll stop there and put a factorial over 21 factorial, because then these two terms would become a factor of 1. So this is just a little bit more compact notation we might use to express 27 times 26 times 25 times 24 times 23 times 22. But if you left it in the expanded form, that's okay too. Let's consider another list. Let's make lists from the letters in the word snowflake. So let's consider how many length 5 lists are possible if repetition is allowed. So we need a length 5 list. There are 5 slots to be filled, and we can repeat letters. So in the word snowflake, there are 9 unique letters. So the number of options we have for the first slot would be 9. Because we're allowed to repeat, the second slot would also have 9 available choices, as would the third, the fourth, and the fifth. So the multiplication principle tells us that we would have 9 to the 5th possible 5 length lists. Now, what if repetition was not allowed? Again, our 5 slots. For the first one, we would have all 9 letters available to us. But as soon as we've used one, the number available for the second slot decreases by 1. So there are 8, then 7, then 6, then 5. If we use our notation from before, this would be equivalent to saying 9 factorial over 4 factorial. Now, let's take it one more step. How many length 5 lists are possible if repetition is allowed and the list must contain exactly 1 W? So again, we can start with our 5 slots. There are many cases to consider. The first is maybe the W is in the first slot. Now, how many letters are available for the second position? That would be 8. And then 7, pardon me, that would be 8 again because we're allowed to repeat. And then 8 again, and then 8 again. So in this case, there would be 8 to the 4th possibilities. But that's not the only place we could have a W. Maybe the W is in the second spot, in which case that leaves us with 8 possibilities for all of the other slots. So again, 8 to the 4th. Where else could the W go? It could be in the 3rd, the 4th, or the 5th slot. So in total, we would have 5 times 8 to the 4th possibilities for our length 5 lists in this case. Now let's consider the same scenario, but repetition is not allowed. So again, our 5 slots, we can consider what if W was first. Then we would have 8 possibilities for the second letter, then 7, 6, and 5. And again, maybe the W is in the second position, which would still leave us with 8 times 7 times 6 times 5 possibilities. And as we continue considering the W moving through the 3rd, 4th, and 5th positions, ultimately we would have 5 times 8 times 7 times 6 times 5, or 8 times 7 times 6 times 5 squared as our final answer. Now that you know about lists and counting how many different lists we might have of different lengths, you can solve a large number of problems. That's all for now. Thanks for listening.